Now let us define the rules of the field B. We know from electrostatics we have this equation where E is the electric field, rho is the volume charge density, epsilon 0 is the permittivity of free space. So in analogy to this, one may be tempted to write in magnetostatics using the field B a constant Km multiplied by rho m. Rho m may be called as a magnetic charge, or in real words magnetic monopoles. But you see, till date in experiments magnetic monopoles could not be discovered. Magnetic poles north and south always appear in pairs. So magnetic monopoles does not exist and the right side must be equals to 0. So in magnetostatics we have this equation. This equation can be proved by rigorous calculations, but as of now let us continue with this crude derivation. Now what does this equation physically means? Divergence B equals to 0. To understand this, let us consider in a certain region of space a closed surface enclosing a volume, say V. In that region of space, say there is a field B, maybe uniform or not uniform. There will be lines of force due to the field B. Then what this equation means is divergence B equals to 0. Suppose we perform a volume integration on this equation, then by Gauss's divergence theorem this may be written as the closed surface integral of B dot dA equals to 0. What this means is integration of the component of B over the entire surface is 0. That means the total number of lines of force entering the surface and total leaving out are equal. That means the lines of force are continuous and there is no sink, either no sink or no source within the surface. This basically means that magnetic lines of force are always closed loops. For example, let us consider the case of an electromagnet, say a solenoid. So when we supply an electric current to a solenoid, a magnetic field will be produced. Say this end creates a north pole and this end creates a south pole, although the polarity will just depend on the sense of rotation of the coils in the solenoid. Then the magnetic lines of force will be like this. You see, the lines of force are always closed loops. It does not terminate either at the north pole or at the south pole. This physical scenario is indicated by this equation. Because the lines of force are closed loops and are unending, that is why the closed surface integral of the lines of force is always 0. Same thing happens for a bar magnet. Now again, from Maxwell's equation we have curl B equals to mu 0 J plus mu 0 epsilon 0 del E del T, where E is the electric field. Now for a steady current we have del rho del T equals to 0. That means the volume charge density does not change with time. So obviously the electric field produced by this volume charge density rho will also not change with time. That means del E del T will also be equals to 0. So for the case of steady current, we have this equation. So these are the two equations followed by the magnetic field vector B. Again note that if we take divergence of this equation on both sides, then we will get 0, which is basically the condition for steady current. As I have already mentioned this equation, B dot dA, this quantity is nothing but the surface integral of the magnetic lines of force over a certain surface S. This quantity phi is called magnetic flux. Magnetic flux is nothing but the number of lines of force of the magnetic field B crossing a certain arbitrary surface perpendicularly. That means here we have a dot product. Definition of flux is the same in every case, for also in light or maybe in electrostatics. So this phi is the analogy of that flux in magnetism. So we have this equation phi equals to surface integral of B dot dA. Inversely, we can also write B as d phi dA. That means B is the number of lines of force crossing unit area held perpendicularly. That is why this B is called, as I have already mentioned in the beginning of the class, the B is also called magnetic flux density. Now let us define the units of the magnetic flux phi and the field B. So in SI system, the unit of flux is called as Weber. The unit of field B is thus called Weber per meter square, which is also called Tesla. In CGS or EMU system, EMU is called electromagnetic unit, basically a CGS system. In this system, the unit of magnetic flux is Gauss centimeter square, which is also called Maxwell, and the unit of field B is simply Gauss or Maxwell per meter square. Now the interconversions are between CGS and SI unit. 1 Tesla is equals to 10 to the power 4 Gauss, and here 1 Weber equals to 10 to the power 8 Maxwell. The next is Weier's law. Weier's law gives the magnetic field B to be calculated at a field point say P at a distance R from a current loop. So now let us consider a current loop through which a current I is flowing. Suppose this is a small length element dl in the circuit. This length element is assumed to be placed at the origin. So at the radius vector r from this length element where we have our field point, we want to calculate the magnetic field B. So the field is given by the Weier's law as mu 0 by 4 pi integral of I cross r unit vector by r square to dl prime. We normally use a prime to denote source coordinates. That means the quantities which is placed at the source, because of which the effect, that means the field here, is produced. This equation can also be written as mu 0 I by 4 pi integral dl prime cross r unit vector by r square. That is because the direction of current and the length element dl prime is the same. So you can note here that there is a 1 by r square dependence of the magnetic field B, just similar to the 1 by r square dependence of the electric field that we learn about in the Coulomb's law. So this Biot-Savart law plays the same role as Coulomb's law in electrostatics. Now, using this law, let us calculate the magnetic field at a distance d from a finite current carrying conductor. Say this one is our conductor of finite length. Within this conductor we have a length element dl. From this length element at a certain radius vector r, there is our field point P. Now we extend this line and this field point P is at a perpendicular distance d from the axis of the conductor. Say this angle is theta. Now the angles of the extreme ends of the conductor may be taken as theta 2 and this one is theta 1. So this angle is alpha, and the length element, that means from where the point from which we are taking the radius vector r, is at a length L prime from the origin. So now we have a current here I. So the magnetic field will be mu 0 I by 4 pi integral of dl prime cross r by r square. First we need to calculate dl prime cross r and its magnitude. So this will be, since the angle is alpha, this will be dl prime sine alpha, and this angle is theta, so this will be equals to dl prime cos theta. Now why I have written cos theta? That is because sine alpha, say if this angle is psi, then sine alpha will be equals to pi minus psi, and again from this triangle Psi may be written as pi minus pi by 2 minus theta. So sin pi minus psi is and sin pi by 2 minus theta is cos theta. So that is why we have written here dl prime cos theta. Again, from this triangle, this one, L prime is equals to d tan theta. So differentiating this one, we get dl prime equals to d sec square theta d theta. So putting this one here, we get d by cos square theta cos theta d theta, d by cos theta d theta. Now again, from this triangle again, r means we have for r cos theta equals to d. So from here we get 1 by r square cos square theta by d square. So finally substituting all these values in the main equation, we will get for the magnitude of B this comes out to be integral of cos theta d theta. Now see, the limits of the integration will be from theta 1 to theta 2 due to the finite length of the conductors. So from theta 1 to theta 2 we get mu 0 I by 4 pi d sin theta 2 minus sin theta 1. So this is for the finite length of the conductor. Now if in case the conductor was of infinite length, then just this theta 1 will extend to infinity. That means we will have to put minus pi by 2 in place of theta 1, and theta will to 2 will extend to infinity along the positive z direction, and we will substitute, we will put pi by 2 plus pi by 2 in place of theta 2. So in that case, for the infinite case, the B will be mu 0 I by 2 pi d. Now let us consider a conductor, current carrying conductor placed perpendicular to the plane of the board, and current is flowing outwards from the plane of the board. In that case, the magnetic field lines will be like these concentric circles. This will be given by the right hand thumb rule. which gives the direction of the field B. If the thumb points towards the direction of the current, then the sense of rotation of the other four fingers will give you the direction of the magnetic field B. So this one is the current I. So immediately looking at the picture, you will see a rotational nature of the field B. So the curl of the field B must be non-zero, as we have already calculated and discussed previously, that curl B is equals to mu 0 J. Now we know for this infinite conductor, if the conductor is considered to be infinite, then say at a distance D we have the field point P, then B at the point P is given by this equation mu 0 I by 2 pi d, as we have already just calculated. Now let us calculate the line integral of this field B over the entire loop indicated by this line of force, the outermost line of force. So we want to calculate B dot dl, closed line integral, and this will give mu 0 I by 2 pi d, since at every point this dl vector and B vector are pointing along the same direction. That means the cos theta of the dot product is cos 0, and that is 1. We can directly write mu 0 I by 2 pi d integral of dl, integral over the closed loop. So integral of dl will be simply 2 pi d, and we get mu 0 I. So you see the line integral of B is independent of the diameter d. That means the size of the circle we are considering. This is simply because as one goes further from the conductor, the deduction in the strength of the field B is exactly balanced by the circumference of the circle, circumference of the concentric lines of force created by the field B. So this equation is known as Ampere's law. Now this closed line integral on the left hand side may be written as surface integral of B dot dA using Stokes law, and on the right hand side the current may be written as surface integral of J dot dA, where the surface S is nothing but the surface defined by the closed loop B. This loop is also called Amperian loop. I forgot to mention that the loop that we considered in the calculation previously is a perfect circle, but that loop need not be a perfect circle. Any arbitrary closed loop will give you the same result, and any such loop considered for line integral of the field about an infinite wire is called as the Amperian loop. So from this equation C, since the surface is arbitrary, so we must equate the integrands, and this will give you our previous equation, curl B equals to mu 0 J.